have to go to the side. So you reach what we call the Chard-Langmuir regime. Right now the current sort of saturate, there's so much you can take out of the fiber. So indeed, and there's an equation for the Chard-Langmuir equation, and it fits well. So we have been able to show that as we increase the bias here, the space charge limitation until eventually it becomes so hot, and if you are too close, you kill the fiber. Here's another plot which has a scale-up version of this. So this is just the corner, and this is the full regime. So what's happening is this. You emit from the tip, forward ordained, fine. You have a plasma in front of the top, it saturates. So what does it do? Emit from the side. Emit from the side, it's another forward ordained from the side. And even the side saturates. And then the whole fiber is basically, there's so much you can get out of it. Now, they bought also a thermal imaging system to see how hot it gets. Okay? So you can see that fiber was also cut with a razor blade, and it's not perfect at the top, but you can see the fiber here, right? And this is our, this shouldn't be kilovolt, it should be volt, but the kilo is 280. So you are approaching the top, because the maximum you can put is 1000 volts, and this is the maximum current you get out of it. Remember, we are shooting for 10 milliamp. So before this happened, no matter which fiber you use, Rice, Cambridge, or here at UC, it always saturates to 2-3 milliamp. We have a tough time getting the 10 milliamp. And you see the reason why. The infrared camera tells you that thing is getting very hot. So you are killing your tubes, basically. So how do you avoid that? Is to try to make sure the tubes will be more uniform. Because in the picture I show you, some of them are very long, some are very tiny. So the long one will burn first, leaving the tiny one to do the work. So if you go get something which they all kind of look alike, they would all contribute the same way to the current, and maybe they would be able to withstand a larger bias, and therefore be able to give you the 10 milliamp. So that's a goal, and after 2 or 3 years, they have not been able to do it. So even though they tried, as I said, to put a few of them up to 5, but then when they are getting too close, they just fly off like a bouquet, like it just never works. Now this is a temperature profile. How hot does it get? Well, the room temperature is 27 degrees C, right? So across that, a different current, you can see that it can reach 400-500 degrees C, okay, which is not negligible, right? And that's why some of them eventually detach from the tube or just burn out. Now, the student I have so far tried to model that. I'm not going to the detail, but the temperature along the fiber will basically obey a differential equation. So something will tell you how it varies as a function of x. 2 contributions, Joule heating, because you heat up the fiber. But then the fiber gets hot, right? So you emit, basically you have emission from the side. So you have basically something equivalent to thermal heating, right? Thermal release, like a black body radiation, basically. Right? It's like a tube sitting in a cavity. And if you took the class in quantum systems with me, you know it's still in power 4. So it means that the temperature is going to change, the contribution will be quite important. So how to model the current? This is a true forward ordained expression, the one I showed you before, with all the fancy detail into it. So the student is doing this. Then what do you say? Well, the temperature of the chuck it's sitting on is the room temperature. Joule heating, you can recognize Ri squared, correct? So this is as the heat you feed it into the tube. And at the top, you can say that the tube, the heat removal from the top is not much. Then you can show the temperature at the top of the tube will go as I squared, L squared, and R to the 4th power. So this is very important. The length of the tube will matter, the current you try to emit will matter, but the radius of the tube will matter. So when you form those nanotubes, you may have some with 2 nanometer diameter, you have some with 10 nanometer, but this is raised to the 4th power. So it means if you have a bunch of tubes which are not alike, they won't have the same L, they won't have the same R, therefore the temperature of their tip will be different. This will affect the current emitted, and that's what leads to that noise, and eventually to the killing of the tube. So which one will suffer the most? The one which are the longest and the narrowest are going to heat up faster to a temperature where the tube could melt. So nanotube melting temperature is 2000 degrees K. So all you need to do is find out when it's 2000 minus 300, the room temperature, equal to this, and it tells you when the tube will melt. So what we did is Monte Carlo simulation of that. So I'm going to show you results at 6 and 8.10 to the 4 volt per centimeter. So this corresponds roughly to 1,000 volts across a few hundred microns. So we say, well, what if we have single wall nanotubes, which have a radius varying anywhere uniformly between 2 and 5 nanometer, and the length could be anywhere between 1 and 10 microns, to sort of mimic that SEM picture I showed you, where they have like different lengths and radius. And I'm going to form an array of those. And in this case, to not show you too complicated of an array, I did a 10 by 10 array of those. Okay, so I'm going to show you a plot of their location, their height, the enhancement factor, which is basically how high they are compared to their radius, because this will affect the field at the tip, and the field at the tip will affect the current, and the current will affect the temperature. So if I would chop my tubes with a razor blade and look from the top, what I do is divide my thing by a 10 by 10 array, and I say the size of the tube can never be bigger than the size of the array. Right? The maximum radius it can have is d, but I put their center anywhere in here, so they never overlap, right? As if I had chopped them. And you can see indeed, asking for uniform distribution, it's quite random. And then, how about the height? Well, I also choose the height, and I forgot that between 1 and 10 micron. So there it is, in nanometer. So it's kind of like a skyscraper, right? Now, before I show you chopping, now I'll show you this one. Now I'm going to increase the field. So which one is going to emit first? The longest one, right? And the tinier one. The longer it is, the narrower it is, the larger will be the beta. The larger will be the beta, the more current they will emit. The more current they will emit because of that temperature equation, the higher the temperature could get. If the temperature reaches 2000 degree K, I will kill the tube. So the Monte Carlo proceeds this way. You put a random array, you start increasing the bias, you record where the temperature, how the temperature changes. Each time any one of those tubes reaches 2000 degree K, you remove it from the simulation. So you go that from 500 to 1000 volt, you keep chopping the tubes as their temperature reaches 2000 degree K. When you are going to sweep down, of course, instead of having 100 tubes, now you may get only 65, right? So you should see the hysteresis. So here is a field enhancement factor. So it's low beta, medium beta, yellow, high beta, and red. So the larger the beta, the more they will emit. So which one is going to emit first? 1, 2, 3, 4 out of 100. Okay. And as you increase the bias, maybe here, this is the current plot. So in succession, the cross section, how they look like, their height, how big is the enhancement factor, which determine the current. So look at this one for a while. 1, 2, 3. Now look at this one. See, it's not the one-to-one correspondence where the current is the highest, it's where the beta is the highest. Right? You have to be careful. But it shows you that some of them, it's in micron, have very low current, so they won't contribute much. And out of those 100, I may have 1, 2, 3, 4, 5, which contribute most of the current. As I increase the field, the temperature will reach eventually, the temperature increases. So in this case, the maximum temperature was 700 K. It's still far away from the melting point. Okay, and remember I was doing it for 2 fields. So I'm showing you at 6, and I'm going to show you the same plot at 8 10 to the 4. So let's look at the temperature at 6 10 to the 4 is only 700 K maximum. Now I'm going to show you the same sequence of plot with the electric field increase. So the temperature should increase, right? So same array as before, same height as before, same field enhancement factor as before. Now more current. You can see more tube. There were 4 before. Now I have more like 6 or 7, which contribute larger to the current. How about the temperature? You see some of them have passed the 2000 degree K. Right? So those 3 are going to die. They won't be in the simulation. So if I had done it at 10 to the 8, 10 to the 4, 10 to the 5, a larger fraction of them will actually reach the 2000 K and get killed. So all I need to do is keep record of which one reached 2000 degree K as I move the field and chop them off, and then sweeping down, of course only the lowest, the one with the lowest beta will contribute. So I should get an IV curve which shows hysteresis. Right? So sweep up, sweep down, and then as a function of E field, I record how many of them are being destroyed. So not much, 5, 10%, 30%, and for the maximum field I had up to 50% of the tube being killed. Remember I only did as a 10 by 10 array for illustration, because if you remember my experimental curve were kind of much smoother than this, right? But if I done it over 1,000 tube, those would sort of disappear, right? But I would get a hysteresis overall, right? So it should still appear. So I think we sort of have a model to sort of explain the hysteresis. Now, how good it is, it's really up to, when we do this, to look at an SEM picture, try to sort of guess the range of height and radius, and over what area, and then put that in the Monte Carlo, and actually try to see if we get a better fit with the experimental results. But at least intrinsically, it's able to reproduce the ID characteristic, right, of hysteresis. What do I need to include next? It's what's called the Nottingham effect. I'm not going to do that, it's a little more complicated. It's controversial. So all of this I'm going to skip. I'm just going to conclude here. So, I actually perform some of the field emission measurement myself. Sit there and just sweep up and down, and that's when you drink coffee and eat lunch, because it takes 3 hours, and there are jokes. And then around then you look at the screen and think about how to interpret this. So I spent a few summers at Rothbard, and they were getting fibers from Rice, Cambridge, and UC. No matter what we try, and they are grown very differently, we can never get more than 20 million in a single fiber. So the goal is to say, well, since the Air Force for the military application want 10 million, how do we tell those people at those 3 places, this is what we have to do to get more current? And my belief is try to get something which is uniform, more uniform after you chop it. So just making the fiber is not enough. It's also use a better laser to cut it. See how much the array of what you get at the top depends on the laser energy and frequency you use to cut the fiber. With the goal that eventually you get all of them pretty much the same length. Hopefully when they give it to you, it's pretty much the same diameter. So you have a more uniform array of tubes which all behave the same way, therefore share the same amount of fraction of the current, and able to withstand a larger temperature, which will lead to less hysteresis. And because, of course, if you have a one-time application of those, if the military is for one application, you have the more fiber to work once, that's okay, right? You don't need to sweep. But if you have another application in which you need to sweep back and forth, you would like the hysteresis to be as small as possible, because as you keep doing this, if the fiber keeps changing morphology, the current results you are going to get are going to be different for each sweep. So you need to be able to do this. So I have a PhD student working on a Monte Carlo code I tried to describe. It's called Monte Carlo because you use random numbers the same way when you play the roulette. Right? That's where it comes from. It includes Joule heating in the fiber, which I'll show you with the infrared picture. It includes emission from the top of the side as a thermal radiation. Energy is escaping from the side because the thing gets hot like a black body radiation. And it includes the fact that eventually you get space charge limitation. In other words, you get plasma forming, which prevents more charge to come out. And that's basically it. Yeah. I don't want to go to the Nottingham effect. Nottingham effect is just this. The tip could be the cooling or getting hot depending on the field. But I don't want to go to the details. It's not too complicated, except it's Nottingham was at MIT in 1950, and that effect has been controversial ever since. So including that in the simulation is kind of like asking to be shut down by the referee. Right? So, but it's something which needs to be there. Any questions?
How exactly are these fibers grown?
Well, it's some of them are different process. Some of them they just take some fibers and make them go to a small hole and just like try to make a fiber out of it and just stretch them. And so it's a lot of chemical processing. You try to glue them together. Right? And then I don't know, Dr. Schultz actually made like a sheet out of them. And then it would be used for armors, like for policemen to just stop bullets. It would be very light and just very hard. So basically fibers for coat and stuff like that.
If the main issue is these things getting too hot and then burning down, have you looked into cooling effects? Maybe something similar, like a heat sink on a...
Yeah, you could do that on the side, try to put them on the cooling system around it.
Yeah.
What you could do, since here is a fiber, right, and the chamber it's sitting in is at 300 K.
Right.
So the temperature goes at T, and this is T0. The amount of heat is T4 minus T04. So if you could put a shield, which is a different temperature between T0 and T, so that you have less heat coming out from the side, because you put a shield around it. Or you could put it in a chuck, which is refrigerated.
Yeah.
And when you do the cuts to try to maintain a consistent level, do you just make one cut, or could you get like cuts
with a razor blade, it was very crude. Like I do it myself, you take a razor blade, loosen the fiber after you're sweating, if you get to it, but the razor, one cut.
So I wonder if as it grows, could you keep cutting it as it grew?
Oh no, they grow it somewhere, they send it to us, and we have this long string, and we chop a little 1 centimeter piece out of it. So the bottom piece we don't care, you can do it with scissors because you attach it to the chuck. But the top one, which is going to emit, you try to do it with a laser. So maybe you could do laser, look at the CM, you're not happy, you go back laser, kind of like when you go and get a haircut, you just, first the guy does that, and then he looks at it and says, oh, I better go and chop again, right? So it's the same.
Okay.
But no matter what, so these are a bunch of tubes kind of intermingled. And then, if they are very long, when you chop them, you're bound to get something uniform. They are very tiny, different lengths, which is more than the length of what you are going to use to cut them. You are going to get something which is very non-uniform.
Along with the tube, too.
Yeah.
Yeah.
I'm trying to understand. So essentially, your problem is that you're trying to pass an electric current through a carbon
Fiber, yeah. Fiber.
fiber.
So the fiber is 100 micron, and the tubes are a nanometer. So you have millions of tubes forming that array. But then when you chop, unfortunately, not all of them contribute. You may have 1,000 of them, because these are the longest ones. So you have kind of some of them kind of like mechanical support, they form the fiber, but the one emitting are only the ones standing up. It's like the skyscrapers in New York, right? You have a tiny building, and then you have the Empire State. So those one will emit.
Actually, try and pass it right through, like,
Yeah, you could do that.
like cut periodic, at least that way, at least the ones that have gotten the hottest, you cut the top of the hot part off.
One idea would be to look, see the problem is you look at them and say, oh, I don't like the same picture, let's put it back. But you could maybe shape them, maybe some of them are kind of loose, and the one which are the torus are kind of like
Yeah.
moving out. But 3 milliamp is the best we can get, and you're in 10 milliamp.
And when you're running the current, is that utilizing the fiber? Is when you're running a current through it, or is it more part of the manufacturing process?
No, the fiber can be used for different applications. Here we just want to run current through it using like a lightning rod. Then we put 2,000 volts and 500 micron. And then we want to use it as a kind of weapon where we just would put maybe 15,000 volts. And then the thing just blasts and emits a lot of current. But then you use it once.
Okay.
Right? But, or other application where you do things more smoothly, you want to avoid at least hysteresis. So if you want to reapply it 10 to the 6 times,
Okay.
in a flat panel display or something else.
Keep using it. Yeah.
So that's why you need, whatever you do, whatever current method you need, you would like to get rid of the hysteresis. And what the simulation shows is like, you better get uniform array of tubes as best as you can, otherwise the hysteresis will always be there.
How clean of a cut do you go for, is it?
Well, I showed the best one I showed you picture. Unfortunately, I don't have, I have, but I don't have it here. Pictures with a razor blade, it's really messy. It's like, see, this is the laser. If you do with a razor blade, it's just, because of the blade, this is, you see some of the tubes kind of like heavy, and you push those things down. You know, those people who try to make you, there are UFOs and they go in the field and actually sweep the field. That's actually how the razor blade is what it does. Right? You just push the tube from the side. So So it's not in the right position.